All right, so as a class, we used a random dice simulator to roll 2 dice until we got doubles. And we recorded the number of failures we had, or the number of rolls we had before we got doubles. Okay. All right, so the number of failures or trials prior to the first success is called the waiting time or waiting period before success. We will examine the following questions using both the experimental and theoretical techniques. So what we just did was experimental, right? We're actually doing the trials in real life as opposed to theory. That would be our expected results using calculations, okay? So what is the probability that the first roll of doubles will occur on the 5th roll? All right. So we can definitely look at our experimental results. And then when we do our theoretical results, I will be using our geometric distribution formula that we're going to learn. Okay, but first looking at the experimental. So what's the probability that first roll of doubles will occur on the 5th roll? So we have to find the proportion of our trials where doubles occurred on the 5th roll, i.e. the number of failures prior to success was 4, right? 1 less than when the success happened. Okay, so we're going to say the probability that we have 4 failures and then a success. Well, we need to look at our data. So how many 4s do we have? 1, 2, 2 out of 25. So that's what we can write, 2 out of 25. Just ignore this class results kind of section. That's what we are doing, our class experimental results, okay? So that's all you need to write there. Somebody put that in a calculator for me. What is that as a decimal probability? 2 divided by 25. 0.08. So experimentally, there's an 8% chance that we have 4 failures on average before we get our first success, okay? B, what is the probability that the first roll of doubles will occur on or before the 3rd trial? So on or before the 3rd trial. Make sure you have this down. On or before the 3rd trial, well, that would mean that we can have no failures. So our first success happens on the 1st trial. 1 failure, so our first success would happen on our 2nd roll, right? Or 2 failures, then our first doubles would happen on our 3rd roll, right? So that encompasses the on or before the 3rd roll. So let's count this up. So probability that we had no failures and our first roll was a double. Let's see, we had 1, 2 out of 25 trials. Plus the probability we have 1 failure and then roll a double. There's 1, 2, 3, 4, 5. Was this a 7? I think so. So 1, 2, 3, 4, 5 out of 25. And the probability of having 2 failures and then on our 3rd roll, rolling a double. Do we have any 2s? Yes, 1 out of 25. So that'd be 2 plus 5 is 7, plus 1 is 8 out of 25. What is that as a decimal? 8 divided by 25. Kaylee? Thank you. Okay, so there's a 32% chance experimentally, or based on our experimental results, that our first doubles occurs on or before the 3rd roll. All right. Last question on this page. It says, what is the expected waiting time or number of rolls prior to rolling the first double? So expected kind of means average, right? What is the average waiting time for your 25 trials? Does anybody have an idea of how we might calculate the average waiting time? How would we do that? What's up?
Add them all up and then divide by 25.
Yeah, exactly. We're going to add up all of our waiting times and then divide by 25 trials, and we'll get the average waiting time per trial, right? So somebody add all of those up for me because I do not want to. No, just kidding. But actually, can somebody do that for me, please? Add them all up, and we'll divide it by 25. Okay, 133. Sum of all waiting times. Number of trials. 133, eh? Okay. And then somebody do 133 divided by 25. Kaylee? 5.32. All right, so on any given trial, we would expect to fail 5 times before rolling, or about 5 times before rolling our doubles, or fail 5 times before having a success, okay? All right. So let's kind of compare that to the theoretical probability. That is something you guys will be able to do after we learn the geometric formula, okay? So it's not explicitly in these notes calculating the theoretical probability for this, but it's going to be something that you're going to be able to do. And maybe I'll do it after the lesson on the side. Okay, but we have a different example after this. But okay, let's learn the theoretical probability, just how to calculate it in general. So looking at the geometric distribution formula.
Theoretical probability.
Oh no, we are doing it right now. Okay, sorry. All right, so we're gonna label S as equaling a success. F as a failure. Okay, so we are looking at the same questions. Okay, question A was, what is the probability the first roll of doubles will occur on the 5th roll? That would be the probability we have 4 failures followed by 1 success, right? 4 failures and then rolling the doubles. Okay, so the probability of that theoretically would be to get the failures, right? Remember our big dice kind of pair chart? There's like 36 outcomes. Do you remember that?
Yeah.
How many ways were there that you could get the doubles out of 36? Awesome. 6, right? You could get a 1 and 1, 2 and 2, etc. So the probability of a success would equal 6 out of 36. That's the same as 1 over 6. That means the probability of a failure would be 5 over 6. 1 minus that, okay? So 4 failures and a success. So you get a failure, that's a probability of 5 over 6. Then another failure, and so I'm multiplying another failure, and another failure, and then finally a success. Okay? That comes out to 0.08. So we can compare that theoretical probability to our experimental. What did we get for our experimental? Which one? Was it 0.08?
Yeah.
What did you guys write down? That's freaky. So our experimental is exactly the same as the theoretical. This is not planned, but it's good, right? It shows that, you know, the theoretical, there's some integrity to that, I guess. Okay? So it's usually not going to be that way. Your theoretical will not always match your experimental. It's just expected. It's just a fluke that it happened to be exactly the same. So that's pretty cool. Awesome.
You could say the pieces.
Next question. So in theory, we want to know what's the probability the first roll of doubles will occur on or before the third roll. And we would say that's the probability of having basically no wait time plus the probability of having one roll that's a failure plus the probability of having 2 wait times or 2 rolls that are failures. So if there's no wait times, we don't fail, we just have a success right away. If our first one's a failure and then a success, so that would be 5/6 times 1/6, plus 2 failures, 5/6 times 5/6, times 1/6. Right? Failure, failure, and then finally a success. So doing that calculation, you would get 0.421. And what did we get for our experimental for B? What did we get, Tyler?
0.32.
0.32, so pretty close, right? Like kind of in that ballpark. 42% probability theoretically, but experimentally we calculated it to be 32%. Right, so it's usually going to be around the theoretical, but not often exactly the same. Right, so that's interesting. And then C was just what was our average waiting time. We can't, for our trials, that was just experimental. There's no theoretical calculation we need to do to compare. Okay, make sure you have that down. And hopefully you guys have some room underneath here. I'm just gonna continue writing here. Okay, so this is all leading up to the geometric distribution formula. Okay, we're going to consider x as equaling the waiting time, or number of failures prior to the first success. Number of failures prior to the first success. Okay. So maybe you can see a little pattern in A and B. But in general, the probability of your waiting time being a certain value equals the probability of a failure raised to the number of times the failure happens, right, which is just your waiting time, or x. And then finally you get your first success, so we're going to multiply it by little p, or the probability of a success. Okay, so it's failure, 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 however many times, and then finally your first success. Okay, so that's kind of where that formula comes from. Right? Okay, just another thing to note. There's something called the expected average waiting time. I just said, right, for question C, there's no theoretical kind of counterpart. There actually is. I just missed it when I was reading this, okay? So expected average waiting time for these geometric distribution type questions is actually going to be equal to the probability of a failure divided by the probability of a success. So that's interesting, okay? So theoretically, for our situation, the probability of a failure was 5/6, divided by the probability of a success, rolling doubles, was 1/6. So our expected average waiting time, right, doing that calculation, flipping and multiplying, would be just 5. And what did we have as our expected waiting time, experimentally? What did we write down for number C, or letter C? 5.32, so pretty close to our theoretical waiting time, right? So that's pretty cool. Okay, get some oohs and ahs. Ooh. Guys, we're not moving on until I get ooh and ah. Oohs and ahs, guys. Thank you. Okay, thanks. Okay. Okay, perfect. That was kind of funny. I saw a lot of serious faces and a lot of funny faces, so maybe my jokes are not landing so well, but you know, you live and you learn, I guess. All right. Anywho, okay. Example 2. Okay, a typical network TV station has 12 minutes of commercials per hour. You're randomly selecting stations using your TV remote. A, what is the probability that the first commercial you see will occur on your 6th selection? So now we can use the geometric formula that we just learned. Okay, so A. So our little x, right, that's going to be our waiting time. If our first success occurs on the 6th selection, what is my waiting time? Or what number of trials is, how many failures am I going to have first? 5, right? Okay. And then using our geometric formula, then the probability we have 5 failures and then a success is going to equal the probability of a failure raised to the 5 times the probability of a success. Okay. Okay, so the TV station has 12 minutes of commercials per hour. So the probability you land on a commercial would equal 12 minutes out of every 60 minutes. That actually equals 1/5. And that was what we're going to consider a success, so little p. And then the probability of a failure then would be the probability we land on, or we don't land on a commercial, would be 1 minus that 1/5, or 4/5. Okay? So we're looking for the probability. What's the first commercial we see is on the 6th selection. So the probability of a failure would be not landing on a commercial. So 4/5 raised to 5 times, right? And then times the probability of a success, which was landing on a commercial, which is 1/5. All right. Does everybody see that, or is there any questions? Give me a thumbs up if that's okay. Good. Okay. So put that in your calculator. You should get 0.0655. Okay.
Okay. Do your date.
Let's take a look at B. So hopefully you have room below. What is the probability the first commercial that you see? Everything okay, guys? What is the probability the first commercial you see will occur on or before the second selection? So that would be, well, if we had no failures and got the commercial right away, that would be on the first trial, right? Or the probability we have no failures, or sorry, one failure, and then our success on our second trial. So this encompasses the on or before the second trial we get our first commercial, okay? So all we have to do here is the geometric distribution formula, but twice, for 0 and for 1, okay? So that would look like this. Probability of failure, 4/5, raised to the 0, and then times the probability of success. That was for the probability of 0 failures, okay? And then plus the geometric distribution when the number of failures is 1, or the waiting time is 1, okay? All right, so that would be 0.36. So there's a 36% chance that the first commercial you see will occur on or before your second kind of channel change, okay? All right, and then finally, question C. What is the expected number of selections prior to seeing your first commercial? Okay, so our expected average waiting time equals Q over P, so the probability of a failure divided by probability of success. Probability of a failure is 4/5. Divided by probability of a success was 1/5. Right, because we're defining a success as landing on a commercial. So that would be just 4. 4 channel flips before getting to the first commercial, or on average we'd get to the commercial on the 5th selection.